Okay. So let's take a quick refresher on Datalog programs. It typically has multiple parts. So the input facts are typically representing the known facts. Here, you can use that to represent the edges of a graph. And then the rules specifies like how a fact can be derived. In the end, you have the queries. So this example is for a very simple graph reachability problem. And then you provide those three informations to a regular Datalog solver like Xufli. And then in the end, the solver can answer questions like whether the output fact pass17 is true or false. So these are basically like a general intro of Datalog program. So why do we care about Datalog? Datalog has been widely used in a lot of applications, like information flow analysis, data race analysis, or database migration, data transformation, or knowledge graph representations. So those are good. Datalog is pretty powerful in a lot of applications. But then, in a lot of times, real-world scenarios often involve with uncertainty. So this requires us to combine logical programming with probabilistic inference together. Here is another program which is adapted from the one you saw from the first slide. We can associate each input fact and the rules with a corresponding probability. This kind of program can be handled by a lot of previous solvers working on probabilistic Datalog or like a ProbLog. And then these solvers are trying to answer a different question, which is about the probability of pass17. These are pretty good, and we can actually use this solver to resolve probabilistic Datalog program. But the problem is all those prior works assume that the inputs are independent. But actually, in a lot of times, the real input fact can be correlated. So let's take a look at one example. When the cardiologist is trying to diagnose some heart-related disease, they may have three input facts there to use to do certain kind of inference. And then for two of them, like chest pain and abnormal ECG, those two facts may not be independent. They are actually correlated from the literature. And then there could be another case for using Datalog for set channel analysis. You might have see two facts here. One for encoding program statements like XOR operation. This one simply means like V1 equals to V2 XOR V3. And then you have a share relation saying that these two variables are sharing the same register. So those kind of information are actually also correlated. The reason is because the source operand V2 and the target operand V1 are highly likely to be placed in the same register according to the register allocation in the compiler's backend. So then, given all those kind of cases, if we provide such kind of programs to the existing probabilistic Datalog solvers, they would produce unsound results because they mistakenly assume independence. So this is what we are trying to resolve here. We are trying to propose a probabilistic variant of Datalog that can deal with arbitrary correlations among input facts. And the problem is removing such independence assumption would introduce a lot of challenges. The first challenge is that it would make the probability computation much more complicated. In the earlier case, in all the previous works, when they enforce independence assumption, all the joint probabilities can directly be computed by simply multiplying them together. However, when we are removing those kind of independence, this equation is no longer there. So for instance, given the same example program, those three facts are correlated, so we can no longer simply multiply their probability together to compute their joint. The other problem is that it's typically hard for users to provide the full joint distribution table, especially when you are going to use that for some program analysis tasks. Some of the cases, we would have a very large set of input facts. For instance, in this case, we have 3. And in order to provide a full joint distribution table, you need to provide an exponentially large table. And in many of the cases, it would be too hard and too user unfriendly. So user might only just give us one or some of the partial conditional probabilities they have in mind. And with this kind of partial information, we only have a few marginal and conditional probabilities. In such a case, when we are computing the probability of a query, the ground truth answer we can have is actually an interval instead of a single value. This is not because our solver is imprecise. This is mainly due to the partial knowledge provided by the users. So here, let's take a closer look of our problem definition. So in the left side, there is a Praline program. Similar to ProbLog, we would specify input probabilities. And then we will also specify correlations. So user can declare arbitrary correlations among input facts using the format of conditional probabilities. And then user can also specify rules, similar to the classic probabilistic Datalog solver. Eventually, you want to query the facts and the probabilities. Given such a program, our objective is to actually compute the probability of the query, which is actually a bound. And then we want this bound to be not only sound, but also tight. So soundness here means that any actual true probability should always be encapsulated inside this bound. And to resolve this, we actually provide two methods. The first one is the exact inference, which is working on computing the ground truth probability bounds. And then we also have the approximate inference for a scalable delta exact inference. So you might not know what delta exact is, but don't worry, I will explain that in a few slides later. So let's first take a look at the exact inference. In a high level, we reduce this exact inference to a constraint optimization problem. So the constraints here are mainly used for encoding the correlations and derivation structures specified in the original input Datalog program. And then we also have the objective, which is an expression associated with the query. So in the end, you might want to minimize your objective to get lower bound and maximize your objective to get upper bound. So this is pretty straightforward, and then it works well for small cases. However, theoretically, this one is sharply hard, and in practice, it cannot scale to the larger instances. Mainly because of two reasons. The constraints may get larger, and also the optimization objective is nonlinear. In order to make the whole thing scale to a much larger cases in practice, we actually produce another approximate inference, which has two requirements. We want it to scale to the realistic instances. For instance, there are lots of very, very large scale program analysis tasks encoded in probabilistic Datalog. They may cover like hundreds of thousands of facts. So we want our approximate inference to achieve this kind of scalability. And then we also want it to give precise bounds. So how do we define precision here? It's called delta exact. So it simply means that the bound we computed, L and U, is within delta distance of the ground truth interval L star and U star. So here is a close look of our delta exact algorithm. Our first step is trying to infer correlation types for a pair of facts. And then given such type, we can do the approximate bound computation. In the end, we would gradually refine the bound until they satisfy the delta exact precision. So let's start with step 1, correlation type inference. So this step is mainly trying to infer the correlation between a pair of facts through a very cheaper inference. So two facts can be positively correlated, negatively correlated, independent, or unknown. So here, we don't really need the exact value of this correlation. Only the sign or polarity of the correlation would buy us enough benefits for generating a tighter bounds. So for the correlation between input facts, we would resolve that through constraint solving. For the derived facts, like outputs, we would conduct some static analysis over the derivation graph to address of them. So as for these two mechanisms, they are not disjoint, they are actually working together. So constraint solving first tries to infer more and more correlations between inputs, and then those information are propagated to the static analysis to infer more correlation types. So if the static analysis fails to infer anything new, and then it would safely fall back to unknown type and delegate this to constraint solving sometimes. So this correlation type inference works very hard on generating correlation types, and then this information is provided to the approximate bound computation to get some actual numerical bounds for the probability of the queries. So our second step is basically built on a known technique called fractured inequalities. It is used to combine probabilities together. For instance, if you have two expressions with their lower bound, upper bound, and then you want to compute the probability of their conjunction or disjunction, you can apply these simple rules to do that. So this is pretty straightforward. However, it's not tight, and in actual cases, it's pretty loose. So let's take a very concrete example. If I replace those symbolic values with concrete numbers, then I'm going to compute my bound for the conjunction of the events, which is pretty loose. However, if I happen to know the correlation type information between E1 and E2, I can actually compute a tighter bound by refining my conjunction rules. So then I can get a roughly tighter bound to compute the conjunction of these two events. So to wrap up for the step 2, it is actually utilizing the correlation type computed from step 1 to potentially generate a tighter bound. Okay, so this bound we are generated is guaranteed to be sound, but there is still no precision guarantees. Remember that we want our bound to be delta exact, which means the bound should be within delta distance from the ground truth. So then this inspires us to develop the third step, which is to iteratively refine the bound until they are within delta distance of the ground truth. So let's start with the step 3. We first take a look at the line here. There are two dots here representing the bound we computed from step 2. And then there are also like L star and U star representing the ground truth interval. But they are unknown. We don't know them. We don't know where they are, but we only know like they are inside the L and U. So this region marked by the ground truth is actually a set region. This simply means that this region is jointly satisfiable with the constraints phi. Phi is generated from the exact inference. And then any interval that is intersecting with this green region would be set. And then the remaining region are actually unset. So if you happen to have an interval that is disjoint from the green region, would also be unset. Okay, so let's start from the interval we computed from step 2. We want to gradually increase the lower bound and decrease the upper bound until at some point it is within the delta distance from the ground truth intervals. So here, we first start with a lower bound. Here we introduce a notion called the bound of lower bound. You might see the bound for lower bound is actually L and L1. And then we gradually increase this bound of lower bound. It would eventually turn from unset to set. And then we would temporarily stop here. In the same time, we would apply the same strategy to the upper bound. We would also maintain a bound of upper bound. So this bound would gradually decrease until at some point it also finishes the transition from unset to set. So with this bound of lower bound and the bound of upper bound, we are going to do some binary search to further tighten these two bounds. Eventually, we terminate if the length of bound is within delta. So then the final L minus and U plus would be the sound and delta exact bound we are going to deliver to users. So let's put everything together. We start from the LU computed by the step 2. And then by doing the iterative refinement, so we are going to compute the final bound L minus and U plus. They are guaranteed to be within delta distance of the ground truth bound. Okay, so here is our implementation. We instrument skillfully for Datalog solving, Groovy for optimization, and specify for constraint solving. There are two kinds of benchmarks. One set is from discrete Bayesian networks. The other one is from large-scale set-channel program analysis for cryptographic algorithms. So there are two takeaways we want to highlight for tightness and scalability. For scalability, we actually compared the exact inference and our approximate inference. So the exact inference can only solve 40% of the benchmark. In fact, a large portion of set-channel analysis, they cannot be solved by the exact inference, while the approximate one can solve all the benchmarks. And for 76% of the benchmarks can finish under 100 seconds. As for the tightness, for the benchmark where the exact inference can finish, we can actually compute the precise bound error. So for those ones, we computed the error, which is 0.1% in average. So to summarize those, the approximate inference we proposed is quite scalable and tight in practice. So to sum up, Datalog input facts can be correlated in practice. And if we ignore that, it may produce wrong answers. So our work is trying to resolve this problem by proposing the first probabilistic Datalog framework to support arbitrary input correlations. And we propose both exact and approximate inference. And also we put the QR code for the tool here, so please try it for application. Thank you.
All right, any questions?
Hello. Yeah, nice talk. I'm Shaurya from UIUC. My doubt is that your procedure where you are using the SAT solver and then the binary search thing, I could in principle use that without the first two steps and starting from 0, 1, right?
You mean we cannot start that from what reason?
Yeah, 0, like they are just probabilities. You compute this L and U bounds and then try to refine it. I can also in principle start from L being 0 and U being 1, right? Because all these are probabilities.
Yes,
so that
but if you start from 0 and 1, that might involve more set solver invocations because you are starting from a looser bound, right?
Yeah, so that's what I wanted to ask. Did you do that ablation and was it giving a lot of, because your bounds are 0.3, 0.8.
Yeah, we have that result actually. So if you so basically you are saying we do some ablation study to remove the correlation type inference, right?
Yeah, exactly. So that was there because it was giving you a lot of benefit, or is just some optimization to get the result fast? It
actually would like increase your runtime for getting the bounds. So that's that's in our ablation study. Okay. We indeed do that by throwing away some of the components like step 2 and 3.
Makes sense. Okay. Thank you. Yeah.
Thank you for the nice talk. I was wondering about whether you support the full Datalog or there's a certain fragment, and if you were to do, say, negation or complementation, how that would affect the efficiency of the runtime.
Okay, so we indeed support a negation, but we restrict the negation should be stratified in our probabilistic Datalog program. And also the negation have different semantic interpretations in the probabilistic sense as compared to its deterministic semantics.
I see. Do you compare with, say, lobster or scallop or other kind of probabilistic?
Actually, yeah, scallop, the problem is that scallop, they similar to ProbLog. So scallop was originally built from ProbLog. And then they all enforce the same assumption that the input facts are independent. So the value they computed is a single value, which is different from the assumption we are having from the program we are trying to solve.
I see. Thank you.
Maybe the next speaker can set up and we can take one more question. Yep.
Thank you for the great talk. I wonder if there is a asymptotic complexity for the approximate inference.
Yeah, so even though we didn't do that theoretically, so we do that empirically to kind of try to describe the runtime complexities with the size of program gets increased. So from the empirical results we have, the plot is nearly polynomial. So we think it's quite efficient and it's not really solving the sharp p-hard problems.
All right. Let's thank Jingbo again.